Mrs. Shomana Gracia Jacob, ME in Computer Science, lecturer in CPET, Chennai for the past 3 years. She has published 4 national and international papers. She has won Star Achiever Award for academic proficiency.
Welcome to the UGC lecture series in Computer Science. In today's session, we will be seeing about the structured data type that is called union in C. In the last sessions, we had been seeing about structures, pointers, arrays and strings. So, all of them are data types which are defined by the user making use of the already existing concepts in the C programming language. So, union is also one such structured data type. Most of the features of union are inherited from structures. So, when you have studied structures already, understanding the concept of unions would be easier. So, first we will see what is a union. As I said, it is a structured data type. Structured data type in the sense a data type which is not already existing as a fundamental one, but something that is slightly modified according to the user's understanding of the application that is at hand. It allows the overlay of more than one variable in the same memory space. Now, this is what is most important about union. Union allows variables of different types to occupy the same memory space at different times. Overlay, it allows an existing variable that is present in some particular space of memory to be overwritten and another variable to be stored in that same place. And it provides a means by which the memory space can be shared. Now, this is what an overlay does. Already a variable is existing there and you overwrite another variable over it. So, the same memory space is being shared by different variables at different times according to the need of the hour. Whatever variable is currently required, that is stored in the memory space and it is used. So, the declaration of a union, its only difference between a structure and a union as far as the syntax is concerned is the use of the keyword. Wherever you use the keyword struct for a structure, instead of that you will be using the keyword union. So, the same declaration over here, union, followed by a name which is called the tag. You have the opening and closing braces which indicate the members of the union. So, here there are around m members. You can have any number of members, you can have different variables of different data types. The only point to be noted is they should be enclosed between the braces terminated with a semicolon. And then you have the declaration of the variables. Again union, keyword, the tag and how many ever variables you want. So, the same declaration as that for a structure, only difference is the use of the keyword union. Now, the union too contains members whose individual types differ from one another. So, it can have number of variables of different data types. Members within a union all share the same storage area. Now, this is another difference between a structure and a union. In a structure, for each variable you will be allocating separate memory space. If you have integer, you allocate 2 bytes, float 4 bytes and so on. The last session we had seen an example where for a particular declaration 36 bytes were allocated, but that is not the case for a union. In a union, if you have an integer, a float and a double, the maximum memory size that is required by variable, that is allocated as a block for the entire union. Now, that is why it enables us to conserve memory, and a storage area which is big enough to hold the largest member of the union is allocated. So, based on the data type of the variables that a particular union holds, at the time of declaration itself, the maximum amount of bytes required to hold the largest member of the union is allocated. So, all the other variables inside the union, as and how they are required, they will be stored in that memory space and then overwritten. So, this is how the allocation of memory differs for a structure and a union. Instead of allocating memory separately to each variable, you allocate a large memory large enough to hold the largest member of the union. Now, we will see this with an example. Now, say here you are having a union, the tag is ID, you are having the members of the union within braces. One is a string called color which is holding 12 value which is having a size of 12. The other is an integer variable which is called size. Now, basically for integer you require 2 bytes. For a character, according to this declaration, you require 12 bytes because it should be able to hold a string containing 12 values. So, here the maximum storage is required for the string, not for the integer. So, maximum storage value required is 12. So, at the time of declaration of this union itself, the compiler will allocate 12 bytes for this entire union. That 12 bytes is to be shared by the string whenever you use the string, and it is to be the same memory space is to be given to the integer when the integer is to be used. So, that is the difference between a structure and a union, and you are having two variables here for the union, shirt and blouse. So, what are the possible operations that can be done with unions? Unions can be operated in the same way as structures, except for minor differences between the structure and union and the use of the keyword, memory space and all that. Most of the operations that are done are similar in nature. A union can be a part of a structure, or a structure can be a part of the union. You can declare one within another. Both are allowed. That these cases are quite rare in programming, because most of the applications do not require that we need to have a structure within a union or a union within a structure. But just for our convenience, sometimes we may go in for programming with such concepts. They are permissible in C. Such powerful concepts allow the programmers to program using such interlinking and nesting of structures and unions. They can be used with arrays also, and the access part of the members of union, we have already seen that with structures. If it is a general volatile variable, we access it using the dot operator, and if we are going to declare pointer variables to access the members of the structure, we use this arrow mark with the direction, pointer, arrow and the variable name. The same concept is used with unions as well. So, what are the operations that can be done on unions? That is, can they be passed as a variable to a parameter and so on? So, a union variable can be assigned to another union variable. So, this is just the concept of transferring value or swapping values. Just as how we use common volatile variables, A is equal to B or B is equal to C. Similarly, we can take a union variable, as we had declared in the example shirt and so on. We can just assign the value to another union variable. This we had seen as an example in structures where we copied elements from one structure variable to another. We can either do it using the assignment operator, or we can take each variable of the structure and explicitly assign its value to another variable, and it can be passed to a function as a parameter, like we had seen passing by value as well as passing by address. Both of it is possible with unions. The address of the union variable also can be accessed using the address operator, which is nothing but the ampersand operator, and a function can accept and return a union or a pointer to a union. So, all the possible operations that are generally done using volatile variables. Volatile is nothing but the default variable, like you say integer a, b, that is a volatile variable, that belongs to the fundamental data type. Similarly, using union variables also, passing arguments to functions, passing them by value, passing them by address, obtaining their size using the ampersand operator, returning a pointer to a function, all these operations are possible with unions. Now, we will see one example program of using a union with a structure. So, here you are having the main function, under that you are declaring the union. Union is a keyword, ID is the tag, it is having two variables, two members, character and integer. Here if you see, color is not a string, you are having only one character, color. Only if there is an array of values here, it is called a string. So, the compiler will understand that this particular variable requires only 1 byte for storage, because the minimum default requirement of storage for a character is 1 byte. The second is an integer variable which requires 2 bytes. So, the time of declaration of this union, the maximum amount of memory required to hold the largest member of the structure only is allocated. So, according to this example, the largest member is the integer. So, 2 bytes will be allocated for this union. The union is closed over here, no variables are declared, and then you are having the declaration of a structure using the structure keyword. Here no tag is mentioned, because here we are not going to use structures. We are just defining a structure, under that we are using this union keyword. Union ID, ID is the tag, DES is the variable which is created for that union, and under this you are having shirt and suit, which are nothing but variables of this struct. So, this is the way you declare or define a union inside a structure. You already declared a union there, you have given the tag and the members of the union. Here you are declaring a structure using the struct keyword. and you are giving its variables and you are declaring the union within this structure. And the two variables for this struct are shirt and suit. So, here if you see printf size of union id. So, size of is already an operator which we have seen. So, here it should return the value 2 bytes because size of is nothing but the size that is required to hold the union. According to the compiler, the memory which is required to hold the largest member of the union alone is allocated. So, we have already seen the largest member is an integer. So, we are just trying to find out whether our understanding of the union concept is right. When we give the size of operator, it will return the memory space that is allocated for this union. And in the next step we see shirt dot des dot color. Now, what is this shirt and what is this des? The shirt was already seen in the declaration of the structure, the variables of the struct. Using the variable of the struct only, we will be able to access the component of the tag. Now, look here, the previous slide we have seen that des is the variable of the union. So, using this des only and the structure variable, using the structure variable to the des variable, we will be able to access the components of this union. That is why we used shirt dot des dot color, again shirt dot des dot size. Then the next variable is suit, suit dot des dot color, suit dot des dot size. So, this is how you access the members of a union even though a union is declared inside another structure. So, first we have obtained the memory allocated for the union. Next we are initializing the value for the member of a union. Color is a member of a union, des is the variable of the union, shirt is a variable of the structure. So, because the union is present inside the structure, using the variable of the structure shirt, we are accessing the variable of the union des and the structure of the union and assigning a value say w. Now, we should remember that always while declaring unions, at a time only one variable of the union can be initialized with a value. This is because only one memory block is allocated for a union. So, at a time only one variable can be stored in that memory block. After that variable is removed from the memory only, you can initialize another member of the union with a value. So, here if you see in this line, I am initializing only one of the members. There are two members in that union, one is color, the other is size. Here in the first step I am initializing only the color. So, next time printing the values shirt dot des dot color, shirt dot des dot size. One important point to be noted here is only color is having a value, size is not having any value. So, what will be printed? The next step I am initializing only the size and not the color, and again I am printing both the values. Now, we will see after the break how the values are printed and how the values are accepted by the compiler. Welcome back after the break. So, we were seeing an example program on the use of unions within a structure. So, here in this program we had seen about the printf statement, where we had just initialized one variable of the union with w, printed both the variables, initialized the second variable of the union with a value and printed both the variables. Now, we will see how the compiler prints these values and what is the value of a variable whose value is not known. So, this is the output of the previous program. Here if you see, 2 is nothing but the size of union. As I said, the size of is used to obtain the memory allocated for a particular variable. The memory required for the largest member of the union is allocated. The largest member of the union was integer, so 2 bytes. That is why the first size of has been printed as 2. The first output has been printed as 2. The second output, if you see, it has printed the value w and minus 24713, which is nothing but a garbage value. W is the value we had assigned to the first variable of the union, but we printed both the variables of the union, both the members of the union were printed. So, because the first value alone is initialized and the compiler knows the value, it has printed it correctly as W, but the second member of the union was not given any value. That is why the compiler has taken some garbage value and it has displayed it. So this color is alone having this value W. So that alone was printed correctly, whereas the size garbage value was printed. Similarly, in the next statement, we had initialized only the second member of the union with an integer value 12. The first member of the union is now overlaid by the second member. So the W value is now no more held by the memory space. It is overlaid by this integer value 12. That is why we say always the memory space of a union is shared by the variables. So when you are printing the next statement, the integer value is correctly printed because its value is known, whereas the color value, that is the first member of the variable, has now lost its value because it is overwritten by this integer. So that is why the compiler again prints some garbage value at the rate of. So this is how unions and structures can be used, this is how they are accessed, and this is how memory space is allocated for a union, and how the compiler prints the values whose values are not initialized explicitly by the user. We need to remember here that always only one member of the union can be assigned a value at any given time, and the member of the union which is holding a value actively in memory is referred to as an active member of the union. Now a union variable, for it to be initialized, its storage class, that is, it has to be declared as either external or static. We have already seen the storage classes of variables. We have auto variables, external, static and register. So only if the union variable is external or static, it can be initialized. Only one member of the union can be assigned a value at any one time. This we have already seen from the previous program. And a member of a union which is functional at any given time is called the active member. So in the previous program, the first time the active member was color, the second statement the active member was the size, that is the integer value. Now we have a few points on which we compare between a structure and a union. First is the memory space. In a structure, memory space is allocated to each variable, to each member individually, whereas in union, the member which needs the largest value of memory is allocated a whole block of memory, and that one block of memory is shared by the other members of the union. In a structure, all the members of the structure can be initialized at one particular time, whereas in a union only one member can be initialized at a time. And there is no concept of active members in a structure. All the members are active as long as they are being used by the user, whereas in a union at a time only one member is functional, so only that member is called the active member. Now memory conservation is not at all rampant with structures because you are allocating the maximum amount of memory for every variable, whereas in a union you are saving the memory space by allocating one block of memory to hold the largest value, and all the members of the union, they share that same memory space as and how they are required. So this saves a lot of memory space for the union members. So when we are using the union, the members of the union can be shared and they conserve and save the memory space without causing much of wastage. The keyword usages: when you are using structures, you use the struct keyword. When you are using union, you use the union keyword. So these are the common differences between a struct and a union. So with that we complete the concept about unions and their usage with structures. Next we move to this dynamic memory allocation. Now there are two types of memory allocation in C. One is static, one is dynamic. Static is nothing but once you allocate the memory, you do it even before you know how much of memory is actually required. If you say integer, you are just giving them 2 bytes. If you say double, you are just giving them 8 bytes. You actually never know whether really those 8 bytes are used at all ever in your program. But it is simply allocated and it remains like that. Neither is it being used by that variable, neither is it available for other variables to use it. So when you are using a large program or running a large program and a large amount of memory is required, such wastage of allocation is not advisable. You need to have a large amount of memory for you to run your program. So in such cases, there is a concept called dynamic memory allocation, where at the execution time, during runtime we call it, the amount of memory that is explicitly required for that particular application alone is given to that particular variable, and once its execution is over, you can release that memory back to the memory space. So that is the concept of dynamic memory allocation. Static is it is already done and it remains the same. Dynamic is at execution time, when you are running the program, you allocate the memory based on the requirement. So the process by which required memory address is obtained without any explicit declaration. Explicitly you do not declare that you have to allocate so many bytes. According to the requirement, memory is automatically allocated. Here you have certain functions which are predefined. Using those predefined functions only you are going to allocate the memory. It returns a pointer to the block of memory of requested size. So, how is the memory allocated? Using a pointer variable. When you are using the memory allocation function to assign memory to a variable, it returns a pointer holding the address of the first block of memory. And these functions are included in the header file stdlib.h, that stands for standard library. So, like in normal C programs we use stdio.h. When you are using the dynamic memory allocation, all your programs should have the header file stdlib.h. So, these are the memory allocation functions. In that malloc, calloc and realloc are used for allocating the memory. Free is used for releasing the memory. So, now we will see how each of these work. All of them allocate the memory, but the thing is they do it slightly differently. Malloc allocates a single block of memory to store values of specific data types. So, this is something like a union where it stores a single large block of memory for a specific data type. So, it can only store either for integer or for float or for double or for character at a time, and it stores and it just allocates one block. The syntax for this is, as I said, it returns a pointer value. So, it has to be collected by a pointer variable. Type star, whatever type, integer or float, followed by the dereference operator or indirection operator. Malloc is a function, within brackets the size. So, this is an example, integer pointer variable, that pointer is equal to the pointer type followed by the indirection operator within brackets, followed by the memory allocation function malloc, followed by the size. If you do not want to explicitly mention the size as 20 or 40, the second example can be followed, like how many variables of type integer. So, the same concept is used, only thing within brackets you tell the data type plus the number of variables of the data type. So, if there are 10 variables, 10 into size of int. So, instead of you calculating the total amount of bytes, a compiler will calculate it and it will allocate the memory. So, both ways you can allocate memory for this malloc function. So, malloc is nothing but allocating memory for a specific data type, and this is the syntax. Now, calloc function works slightly differently. This also allocates memory, but in multiple blocks of the same size. So, in malloc it allocates one full block for the maximum size. This allocates multiple blocks of the same size. So, instead of allocating 20 blocks as such, it is not identified by the pointer as one continuous block of 20 bytes. It is identified by the compiler as 4 blocks of 5 bytes each or 5 blocks of 4 bytes each, which totals up to 20, but each block is identified individually. It assigns the address of the first byte of the allocated area to the pointer. So, though 20 bytes are allocated, the first byte of the first block of the memory only the pointer holds the address, and they will be continuously stored in memory. The same syntax, only thing instead of malloc you use the calloc function here, and within calloc you are having two arguments. One is n, which shows the number of blocks to be allocated, and m is the memory size of each block. As I said, it can be 5 blocks of 4 bytes or 4 blocks of 5 bytes. So, n determines the number of blocks, m determines the size of each block. So, we will see that with an example. Float, pointer variable. So, this also stores the variable stores the memory only for a particular data type, which you have to explicitly mention. Pointer, float, indirection operator, calloc 20, 4. So, what is 20? 20 is nothing but the number of blocks. 4 is nothing but the size of each block. So, 20 into 4, totally 80 bytes of memory are allocated. Another option here is again calloc 20. 20 is the number of blocks into size of float. This is similar to the malloc function, where instead of you yourself telling the size of a data type, you allow the compiler to decide it. So, this is how it is stored in the memory and it is identified by the memory. This pointer variable holds the starting address of the first block. The starting address of the block is 200, so that is held by the pointer variable. And then each block of memory is of the size 4. That is why 200 to 204, 208, 212 and so on up to 20 bytes each. So, totally 80 bytes are there. So, up to 276 you store the values. This is how using a calloc function the memory is allocated. Realloc is nothing but reallocation of memory. So, malloc and calloc are used for initial or the first time allocation of memory to variables, whereas realloc is used for already memory is allocated, but you want to make some modifications in that, you want to reallocate that memory from the existing memory space to somewhere else in the memory where it is free. So, this modifies or reallocates the memory space previously allotted. It is also called reallocation of memory, that is a short form of realloc. The syntax, the same syntax here, pointer variable is equal to realloc, but within brackets again you are having two arguments. One is the pointer variable itself. Why? Because you should know where the previously allocated memory is existing, and next the size, how much of memory is to be reallocated. So, the example here, integer pointer variable p is equal to the data type malloc 50, that is, it is showing that this is already allocated memory. So, using malloc you are allocating some memory and storing it in the pointer p, and next using the realloc function you are getting the first allocated address which is stored in this variable p, and earlier 50 bytes were allocated. Now, you are going to allocate 100 bytes and again store it in the same pointer variable. So, this is just an example where already allocated memory is being reallocated using the realloc function. Earlier 50 bytes were allocated, now 100, and the size or the pointer where the first allocation was done, that is also held over here. The new allocation is also stored back in the same pointer variable. So, this is the concept of the realloc function. So, next we move to free. Free is nothing but release of the memory. So, this releases the memory space that is allocated using any one of the memory allocation functions. Now, you should remember that memory that is allocated using the dynamic memory allocation functions only can be freed by this free function. The syntax is just free and the pointer variable that holds the address. Now, what are the advantages of this allocation functions? It uses memory without wastage. Right at the time when we need the memory only we use it. The requirement of memory is not necessary, that should be known in advance. When we are running the program, depending upon the variables input by the user, it will allocate the memory. It has a very simple syntax. Now, this is just a small example program. We have used the library.h file, the main function, and a float pointer variable. Using that, we are allocating the size for that particular float variable, malloc size of float, and that is stored in the pointer variable fp. Now, we are printing the address of the memory that is allocated. So, it has now been stored somewhere in memory. We are trying to get that address from the compiler. Then we are entering a float value, we are accepting that value, and now we want to see the value that is stored at that address. That is why here we are simply using the variable fp to get the address. Here we are using pointer fp to get the value. So, this is how the value is printed. First the address is printed, then the float value that we have entered, then the value is stored correctly at this particular address. So, this is how we use malloc functions in the dynamic memory allocation functions in the C programming language. So, the possible questions that can come in this session are the features of the union data type, where you have to mention about the declaration features, the memory conservation features, and how it is different from a union. What are the major differences that we have already seen in memory space and in the usage of keywords and in the initialization of members, the presence of the active member. Dynamic memory allocation is allocating memory at execution time without wastage of memory when the actual requirement of memory space is known. The available functions are malloc, calloc and realloc. Free is used to release the allocated memory. And the use of the active member while operating with unions is, it is a job of the programmer to remember which is the member currently active with the union, because only that member will be holding the actual value. If you are going to do some program or some calculations using a non-active member, it will lead to garbage value. So, that is the importance of the active member when we are working with unions. So, in today's session we have seen about unions and dynamic memory allocation. So, most of the concepts that occur in the language C, from the basics through the tokens, the basic elements of C, the character spaces, the sets, the operators and expressions, functions, pointers, strings, arrays, structures and unions have been covered in this C session and the example programs for each. So, as we work out the more and more example programs, understanding the syntax would be easier for you. Thank you.